The final part of my lecture is on errors in epidemiological studies. Okay, finding from epidemiological studies could be due to chance or random error, bias or systematic error, could be due to confounding or true effect. So what we want in our result is the true effect. Random error refer to fluctuation around a true value because of sampling variability. This is the divergence due to chance alone of an observation on a sample from the true population value. Whereas systematic error is any difference between the true value and that actually obtained that is the result of all causes other than sampling variability. Random error can be problematic, but this can be reduced by increasing sample size, we change the study design, or we improve the instrumentation. Probability of some types of influence can be quantified, for example, using confidence intervals or using p-value. Systematic error or bias is the more problematic. This may be present without investigator being aware. Sources may be difficult to identify and influence may be difficult to assess. Systematic error can be classified into three. First is information bias, selection bias, and confounding. Information or measurement bias can occur when method of gathering information is inappropriate. If misclassification of exposure or disease is unrelated to disease or exposure, then the misclassification is non-differential. If misclassification of exposure or disease is related to disease or exposure, then the misclassification is differential. It will distort the true strength of association. There are many sources of information bias, include subject variation, observer variation, deficiency of tools, technical errors in measurement. Next is recall bias. This can happen when participants are unable to remember in detail of their exposure. Those exposed have a greater sensitivity for recalling exposure. Specifically important in case control studies. When exposure history is obtained retrospectively, cases may more closely scrutinize their past history, looking for ways to explain their illness. Reporting bias. Individuals with severe disease tend to have complete records. Therefore, more information about exposures and greater association found. Individuals who are aware of being participant of a study behave differently. This is called Hawthorne effect. To control information bias in study, it is good to have a standard protocol for data collection. Make sure sources and method of data collection are similar for all study group. Make sure interviewers and study personnel are aware of exposure or disease status of participant. Gather data or information from multiple sources. Form of survey. Mail may impose less wide quotation than a phone or face-to-face interview. Questionnaire. Use multiple questions that ask same information, act as a built-in double check, and multiple checks in medical record. Next is selection bias. Any systematic error that arises in the process of identifying the two study groups to be compared. The wrong people are getting into your study population. Result in the study group being non-comparable unless some type of statistical adjustment can be made. A distortion in the estimate of its effect resulting from the manner in which subjects are selected for the study population. There are many possible sources of selection bias. One is selection of a comparison group or control that is not representative of the population that produced the cases in a case control study, or control selection bias. Second, refusal, non-response, or agreement to participate that is related to the exposure and disease, or we call self-selection bias. Number 3, differential loss to follow-up in a cohort study, such that the likelihood of being lost to follow-up is related to outcome status and exposure status, or loss to follow-up bias. Number 4, using the general population as a comparison group for an occupational cohort study, or healthy worker effect. And number 5, differential referral or diagnosis of subject. Selection bias can only be prevented and controlled during the design and conduct of a study. Control selection independent of determinant status and good definition of sources population. Next is confounding bias. Confounding is just a mixing of effect. the estimate of the effect of the exposure of interest is distorted because it is mixed with the effect of an external factor. To identify a confounding factor, we need to look at the relationship between the variable. To be a confounding factor, two conditions must be met. If we look at the relationship between exposure, outcome and the third variable, confounding must be associated with exposure without being the consequence of exposure. And confounding must be associated with outcome independently of exposure or not an intermediate. For example, if we want to know whether children with a higher birth order more often have Down syndrome or not, is birth order is a risk factor for having child with Down syndrome? Let's look at the relationship between determinant, birth order, the outcome, Down syndrome, and the possible confounding factor, which is age of the mother. First, confounder is determinant of the disease outcome. In this case, confounder or the age of mother is actually determinant of Down syndrome. Number two, confounder is associated with the determinant. The age of mother is actually associated with the birth order of child. Number three, confounder is not a factor in the causal chain, or it's not in between the determinant and the disease outcome. So in this case, age of mother is the confounding effect if you want to study a birth order effect on the outcome of Down syndrome. Another example, if you want to look at the relationship between coffee drinking and chronic heart disease. Possible confounding factor is smoking. If we look at their relationship, smoking is correlated with coffee drinking and also a risk factor of chronic heart disease. How to control for confounders? There are two ways that we can control. First, in study design. In study design, we can use restriction, where restriction of subject according to potential confounders, or we don't simply include confounders in study. Number two, we can do matching, where matching subject on potential confounder, thus assuring even distribution among study groups, example, age, gender and race. And number three, we can use random allocation. We can random allocate all subject to a study group to attempt to even out unknown confounder. However, this can only be applied to experimental study only. And number two, we can try to control confounder in the data analysis. We can do stratified analysis using the Mantel-Hansel method to adjust for confounders. Then we can compare the crude and adjusted measures of association. We can implement a match design after you have collected data, or you can do restriction, which is still possible at the analysis stage, but it means throwing away some of your data. And you can do model fitting using regression techniques. So when you find association in a study, is the association likely to be due to chance? Is the association likely to be due to bias? Or is the association likely to be due to confounding? Or is it true association? Finally, what we estimate from epidemiology study really an association, not causation. Association and identifiable relationship between an exposure and disease, which imply that exposure might cause disease. So a rooster crow associates with the sunrise but does not cause it. So that is the same in epidemiologic study. So how to determine whether association is a causation? One criteria that we can use to identify whether association is a causal factor, we can use Bradford-Hill criteria. There are 9 criteria under this analogy. Number 1 is strength. Number 2, consistency. Number 3, specificity. Number 4, temporality. Number 5, biological gradient. Number 6, plausibility. Number 7, coherent. Number 8, experimental evidence. And number 9, analogy. This is the end of this lecture. Thank you for your attention.